Welcome back to ECE 501B. You have one homework under your belt, and homework number 2 is due similarly to how homework number 1 was due. I haven't done much with what you've submitted for homework 1, but that will be forthcoming. There are a couple of lectures now that we haven't physically experienced in a classroom, but they are available on D2L. One is talking about basis vectors, and the other is talking about dimension. And in terms of basis vectors, that one is what was provided essentially for the Labor Day period, and then dimension follows that. But basis has two properties associated with it that I want you to keep in mind. Basis vectors have, in terms of their properties, they span the entire vector space, and those vectors are linearly independent. So those two properties constitute basis vectors, and that's what is sort of talked about in that lecture. One point that I want to make today is I made an executive decision based on me having a lot of appointments happening at 3:30 on Thursdays. I've decided to go ahead and move, instead of cancel office hours, I've moved those to now 9 o'clock to 10 a.m. on Thursday mornings instead of in the afternoon. And today we are starting Chapter 3. And what I would like to do then is start talking about Chapter 3 topics, which the main theme for Chapter 3 is linear maps. And that's now allowing us to map between vector spaces. We've talked about vectors. Now we can talk about mappings between vectors or between vector spaces. We'll give some properties. These linear maps have two main properties, additivity and homogeneity. It's sort of like addition and scalar multiplication with our vector spaces, but now this pertains to linear maps. We'll look at some examples. Then you can actually create a vector space of linear maps. So these vector spaces can be very generic or very abstract concepts, the concept of a vector space. And now you could take this set of linear maps, and that now becomes a vector space. We'll then talk about a couple of different very important spaces. These would be subspaces associated with the linear maps, and that's the null space, what vectors actually map you to the zero element, and the range space. Where can you arrive, or where can you get to, where can you end up in your output vector space through the mapping, the linear map T. That's the range space. What's the range of that mapping, that linear map T? Let's then start this discussion of Chapter 3 with the following. A linear map is a function, and I know that many of us are visual, and I just like to draw clouds. Maybe I'm always in the clouds, but here are two clouds. We have an input vector space V and an output vector space W. That's what those clouds represent. And now we are interested in the linear map T that maps between the input vector space V and the output vector space W. A linear map, then, is a function, that's this T, capital T, that takes as its input an element or a vector of a vector space, call it V, that's the input vector space, and uniquely identifies an element or another vector of the output vector space of the vector space that we are now labeling W. And we might indicate that more symbolically by saying T is a map such that the vector space V gets mapped into the vector space W. There's our map T, and V to W says we're going from a vector space V to the output vector space W. And the picture that I like to keep in mind is just those two clouds with a map between them. Two vector spaces, V and W. Sometimes they could be the same. Many times they might be the same. But we want to be able to talk about or think about linear maps between two vector spaces. We're now, and if you need something to think about, a linear map can be a matrix. That's something that you can think about. Oh, he's saying linear map. Let me get a concrete example in my head. Oh, that's a matrix. And that matrix could be in many different dimensions, depending on what your vector spaces V and W represent. But these linear maps have two properties, requires two properties to qualify as a linear map. One property is additivity, which means that we might have two vectors in our input vector space, U and V, and if we combine those, which we can do since they're a vector space, we can look at the sum of U and V. If we have a linear map, then the linear map operating on the sum, U plus V, better be the same or equivalent to the sum of the linear map applied to U plus the sum of the linear map applied to V. And that's true for all U and V belonging to our input vector space V. That's one of the two properties, additivity. The second property is homogeneity. And homogeneity now says that if you take a map, a linear map T, and apply it to a scaled vector from your input vector space, then that needs to be the same as scaling the linear map operating on the original vector V. And that's for all of our scalars, A, in our two different fields in this class, the real field or the field of complex numbers, and any vector in our vector space V. With those two properties, that gives us a linear map. Together, these properties make a map linear. And what we might see happening throughout this discussion now of Chapter 3 is I might get inconsistent with the notation that I use. So let me make that as a remark. I may mix, or even the book might mix, notation. By that, I might say, oh, the linear map T operating on a vector V in our input vector space, capital V, I'm going to maybe write that as either T parenthesis V or just TV. And hopefully you won't go home and said all we did was look at TV today during class, because we are going to be talking a lot about TV. But that doesn't mean television. That means the linear map T applied to a vector V. So now whenever you hear somebody say TV, you can think of ECE 501B, and you can just start processing that information. Good reminder, right? Are you going to watch TV tonight? Yes, of course I am. I'm going to be talking about linear maps. T, a map applied to V. And we can also look at saying this linear map could be described by this set, script L, taking vectors from the input vector space V and producing vectors in the output space W. So we're defining this script L operating on capital V, capital W to mean the set of all linear maps T that take vectors from V to W. And L, script L, will obviously depend on what we're starting with for V and W, but once we say L and we identify V and W, then we know that we're talking about the set of all linear maps mapping between those two vector spaces, V and W. We obviously wouldn't be playing with this if it wasn't a very important or extremely, let's say, broad category. Linear map is an extremely broad category. To get us thinking about TV, if we're saying TV, we might like to have some mental concepts in our mind when we hear that linear map term. Here are some examples from the textbook. One linear map could be the zero map. This is a linear map that maps all elements of our input vector space, V, to the additive identity in our output space W. And this may get a little bit confusing because we are actually going to overload this zero, the symbol zero. For example, the zero map I might just label as 0, which is applied to a vector V. Well, that's going to give me 0. But I'm meaning something different on the left-hand side with that symbol 0 and the right-hand side symbol 0. You can tell there's a distinct difference in the notation just there. But I may not make that distinction very clearly in other discussions, but this 0 is in fact a map. It's mapping any vector little v from the input vector space into this 0, which is actually a vector in the output space, and this is a special vector. This is the additive identity. In our output space W. So our notation is what's referred to as overloaded, meaning this same symbol, 0, can take on many different meanings. The same symbol means several things. In one case on the left, it's a map. On the other case on the right, it's a vector. Question? So what we have to worry about here, in this particular, the question was, it's not unique. So you have to basically understand, if somebody writes this down, what are my input vector space and what's my output vector space? Then you should have a unique map. That means V maps uniquely to 0. V1 maps unique. It has a unique map to 0. V2, you take out a capital V. That has a unique map to 0. It just depends what is your output vector space. That will define what 0 on the right represents. And the big 0 on the left is this mapping, and that depends on what you're mapping between in terms of your input vector space. So unique doesn't necessarily mean that it's different, that you're going from a different input, or for each input you map to a different output. That's not what the unique means. The unique means that given a particular input, there's a unique mapping to the output. And that output could be the same point. In symbols, you could sort of say, oh, here's my input vector space, and here's my output vector space, W. What we're saying is, you give me a point here, maybe that's V1, the map is going to go there. And that ending point is actually 0 in W. You give me another vector, V2, and that also is going to go to the same, but these mappings are unique. Okay? And here might be V sub 3, and this is going there also. And these are now the 0 map applied to, so maybe I'm mislabeling these maps because in the past I just labeled them with the linear map, so maybe I shouldn't put that that's operating on, that's implied by what's at the left-hand side of that particular operator 0. That's just one example. That's the 0 map, meaning every vector gets mapped into the additive identity in your output map. Another linear map is, let's say, something that's called the identity map. This maps each element in the input vector space V into itself. And a lot of times we might label that as I. That's now I, which is an element of this set of all maps between V and W. Or you could say that IV is now V. That's the identity map. You start with some vector V in your input vector space, and you map that through the identity map, and you actually end up back at the same point that you started with at your input. The output is the input. And your output vector space W is actually V, the vector space V. Another linear map is the differentiation map. That now says that you are looking at linear maps such that you're taking as far as your input vector space, let's say all the polynomials over the set of reals, and you're mapping that into the set of polynomials over the reals, where the linear map is the differentiation map. Suppose that we take a polynomial, p of x, in capital P of r. And now it's helpful sometimes to just write down a concrete example, meaning let's say that p of x is 3x squared plus 2x plus 7. Pardon? So t now, the notation that I'm trying to use, or that is being used, is t, this linear map, is now an element of, well, maybe what is now an element of the linear map, capital L. Capital L is all of the linear maps that map between this set of all polynomials over the reals into the set of all polynomials over the reals. That's what script L is, and now we're just taking a particular mapping, linear map, out of that collection of maps. And T, we're now saying, is going to be the differentiation map. So now what you're doing is you're taking the set of all polynomials, that's P of R, and you're mapping between the set of all polynomials, and one such linear map is actually the differentiation map. Let me see if finishing the example will help. So we're starting with little p of x, that's a polynomial, out of big P of x, that's what this is saying. And now what happens if I take and operate on P with this linear map T, if T is supposed to be the differentiation map? This is what you had in calculus, first semester calculus. What is T applied to P? Is that result belonging to the set of all polynomials? Yes. So 6x plus 2 is in script P of R, as is 3x squared plus 2x plus 7. And that, so now we're saying that TP, you could say, looks like P prime. Since T is our linear map, which is the differentiation map, if I say TP, that's the same as saying P prime. And we could simply verify that we have this differentiation map satisfying the two properties that are necessary for that map to be linear. We need it to be additivity, or for it to have additivity. If I applied the differentiation operator or linear map to the sum of P and Q, that's okay as far as an expression. By T of P plus Q, that's just saying I'm differentiating P plus Q. What happens if I now differentiate the sum P plus Q? That's equivalent to the differentiation of P plus the differentiation of Q. But by definition of T, what is that? That's TP plus TQ, and that's now what I wanted to show, additivity. T of P plus Q is the same as TP plus TQ. Additivity is indeed satisfied for the differentiation map. What about homogeneity? In this case, we differentiate or apply the differentiation map to a scaled version of the polynomial P. By definition of the differentiation map, that's AP, the derivative of AP, and A is a scalar. It's not a function of X. And that's what we set out to show, that T of AP is equal to or equivalent to A T of P. Homogeneity is true for the differentiation map. And that sort of begs the question, well, if you can do differentiation as a linear map, what about integration? And if we're thinking about integration, are there two sort of categories of integration? If I drew an integral sign, there's sort of two ways I could how do I want to say this? Fancy it up or spruce it up. If I had an integral sign and just left it alone, what would my result be? What would you call that? An indefinite integral. If I had an integral sign and I put limits, that's now a definite integral. So I have two categories of integration, and that actually impacts my output vector space. Meaning, if I had indefinite integration, what do I end up if I integrate a polynomial? Indefinite. So now if I indefinite, no limits on my integral, and I start with a polynomial, let's say P over the reals, what do I end up with? If I integrate the integral of x, what do I end up with? A scaled x squared, right? Plus some constant, and that's belonging to the set of all polynomials. If, though, I looked at the definite integral, and again I start with a polynomial, where do I end up? Now I'm just going to end up with a real number once I evaluate at the lower and upper limits. That hopefully gives you a feel for how your input and output vector spaces obviously depend on the linear map. What about if we had a linear map that is dimension changing? And you might have to go back and return to what we were referring to as dimensions, but here, suppose that we had a linear map T that belonged to the set of all linear maps mapping from R3 to R2. And we haven't gotten there yet, but if we talked about the matrix realization or representation of this, now we would be looking at a matrix that has 3 columns to be compatible with R3, and it has how many rows? To be compatible with R2, we now are looking at matrices that are 2 by 3. if we wanted to find a matrix representation of this linear map. But we don't necessarily have to do that. We can simply say, now we're operating on a vector v that I'm explicitly identifying its three coordinates, x, y, and z. X, y, and z are the coordinates of a vector v where v is living in R3. And what we're saying with this dimension changing, to give us just an example, we might say, oh, we want to go from a 3 vector to a 2 vector. And one way of doing that would say, oh, let's just take some linear combination of the 3 coordinates of our vector v. And there's my first coordinate of the output. And my second coordinate might be 7x plus 5y minus 6z. So that this might be w1 and this might be w2, where the whole thing is our vector w, consisting of 2 coordinates in the vector space of R2. And that's a dimension-changing linear map. And you could go through and verify that this particular map satisfies additivity and homogeneity by picking 2 different varieties for v. And maybe I'm confused. I'm overloading a lot of my notation. Here I'm saying v is a vector xyz, or if it was consistent with what I've done on the right, it would have been v1, v2, v3. And then I just wanted to say, well, pick another vector v, and I was going to call that v sub 2. So do you see how confusing I could make it? Easily. Okay, let's move on then. Try not to confuse, but I hope you see that you're starting with a 3-coordinate vector on the left, operating through a linear map to produce a 2 vector. We're going from R3 to R2. We could also talk about a projection map. By that, you might think of, oh, I now have some point in 3-dimensional space, and I'm going to project that onto a plane in the same 3-dimensional space, but now it's on a plane. Meaning, maybe you would take the following 3 coordinates of a vector v and map those through this linear map T. And maybe what you're saying is, I just want to map onto the xy plane. That would be sort of a very simple way of thinking about a projection map. So if I walk around the room and my head is any point in 3 space, what happens when I apply my position of the head through this projection map? If the floor is the xy plane and z is the vertical, now do you see that this point xyz is moving around in the room, and how is it related to the linear map of the projection? Anytime that I'm in some spot, now my head, no matter what the z was in that particular example, for those of you listening, you missed this dance that I'm performing in class, but you might walk around your room at home and say, what if I go to a different location, x, y, and z, my head is at a spot, but now if I change my z, what happens as I pass through this projection map? I stay at the same xy coordinates. Now do you have a feel for this algebraic operation of txyz is equal to xy0? Now you have this You have TV sitting right in front of you, right? And now this TV is a projection map. You didn't know that TV could be so interesting, did you? Reality TV, even. And it's even more, what? Head. It's more of a exercise in mental activity in this classroom, reality TV, than you might see in the other form, I'm hoping. Okay. But you might say, is the projection map a linear map? Is it linear? We have a lot of different ways of showing things or demonstrating or verifying. If we simply apply a direct proof, then we need to show that additivity and homogeneity are satisfied. In this case, if we look at additivity, what are we letting? Well, let's go ahead and look at two vectors. Let's pick u, and now I am using one of the notations. I'm letting the three coordinates be the subscripts u1, u2, u3, and let's say v is v1, v2, v3. We're interested in t of u plus v. And that's now t of u1 plus v1, u2 plus v2, comma, u3 plus v3. What's the result of this projection operator t? We don't know yet if it's linear, but let's just go with how it's defined. What is the result? What's the size of the output vector? How many coordinates does it have? 3. And what makes up those coordinates? What's the first coordinate? That's just u1 plus v1. The second coordinate, u2 plus v sub 2. And what's the third coordinate? Applying this definition, or how we define this projection, that's now 0. But knowing what we know about vectors, we could write this as u1, comma, u2, comma, 0 plus v1, comma, v2, comma, 0. But that is simply t of u. Well, maybe I'm getting ahead of myself. Let me just go ahead. That's the same as t of u1, u2, u3 plus t of v1, v2, v3. That's from the definition of that projection. Or that's t of u plus t of v, and that's what we set out to show for additivity, that t of u plus v is equal to t of u plus t of v. The other property in the direct proof is to show that this projection operation satisfies the property of homogeneity. And for this, let's just go ahead and let our scalar be an element of, or some element from, our field of numbers, f. If we take t and project, or I'm sorry, if we take alpha u and use the projection operator t on that, that's now t, alpha u1, alpha u2, alpha u sub 3. And what's the result? How many coordinates do I have in my output? I'm retaining or staying in R3, the last coordinate being mapped to 0, and I can actually factor out the alpha. But that's now alpha times t of u1, u2, u3, which is alpha t of u. And that's what we needed to show. We needed to show that homogeneity was satisfied and that additivity was satisfied, which now allows us to say that that projection operator, by a direct proof, is linear. What if I give you another map that I will call the translation map? So now we're having a map T, map between R2 and R2. And suppose that I now define this translation map to be such that if you give me any vector in R2 that I'll subscript u sub 1, u sub 2, I'm defining that map, that translation map, to be, let's shift the first coordinate by 1 and let's shift the second coordinate by 2. And now what I'm wanting to ask is the translation map that I've just defined, is that map linear? What are we thinking? And maybe before I get a show or a verbal, maybe we'll do a show of thumbs again, where up is the map is linear, down is the map is not linear. And I'm going to count to 3, and you know the drill. You show me your thumb up or down up against your chest. Are we ready to answer? Is this translation map linear? And now you're thinking, okay, additivity, translation, or homogeneity. Additivity, homogeneity. Is it linear? All right. 1, 2, 3. Kind of have a mixed bag, don't we? So here's one way to quickly sort of determine if a map is linear. Let's look at creating a counterexample. And one that's very powerful is the additive identity mapped onto itself? Is the 0 vector mapped to the 0 vector? That's one way of quickly finding a counterexample if a map is not linear. The answer actually is no. This map is not linear. And here is a counterexample for that. And in fact, the class was pretty equally split between up and down. So it's not clear from what we've talked about yet how to conclude whether a map very quickly is linear or not. But this counterexample can be used to quickly determine whether it's not. Obviously, if it satisfies this, that doesn't guarantee that it is linear. Is that clear? But it would immediately tell us if it fails this test that it's not linear. Here's the question that we're asking. Is the additive identity which is really just a fancy way of saying the 0 vector, is the additive identity mapped onto itself? from the definition, if I take this translation map, T, and for u sub 1 and u sub 2, I apply 0, what's going to be the output? We're going to add 1 to the first coordinate and 2 to the second coordinate. So if I add 1 to 0, I don't get 0, do I? I get 1. And if I add 2 to 0, I get 2. And what were we expecting? We would like, if it's linear, it actually should have been, 0, 0. So we did not, here's our 0 vector, and the 0 vector on the left did not map to the 0 vector in the output. So this actually violates homogeneity. Let's try to explain this just to make it a little bit more clear why we are able to use this as a counterexample to something, a map, not being a linear map. So here's an explanation for why a linear map should map the additive identity which is the 0 vector onto itself. In general, if you wanted to simply write down the homogeneity property in terms of the map, if I take T and map that, or take alpha V and map that through T, if this satisfies homogeneity, what's supposed to happen? That's supposed to be alpha T of V. And what's one of our propositions from chapter 1? If I take 0 and if I take the 0 map, or let me take that back. This is now from chapter 1. We didn't talk about maps, did we? So what is this big 0 representing? This is a scalar, isn't it? If I scale any vector v by 0, what happens? What's the output, or what's the resulting vector? So that's the 0 vector. So now, that's really what's supposed to be in the argument on the left of that earlier expression. Let's sort of break this down into all of its parts. Let's let A, the scalar, be 0 in our field of numbers. And let's let the vector V be any element in our underlying vectors, input vector space, capital V. So that now, let me just create this string of relationships. Suppose that I now say I want to take a map T and apply it to A times V, where A is 0. What do I know happens internal to the argument or to that vector from this proposition? I have this in my notes from the second edition of Axler, so that's Prop 1.4, and I want to sort of keep track of what I'm using, so that's what I'm going to be saying here. From Prop 1.4, what do we know is the argument of that map T? What's 0 times V? That needs to be 0, doesn't it? So this argument relationship on the both sides of that equality, this is a true statement from Prop 1.4. Is that okay? Now, what do we know about t of 0? Or, how do I want to say this? What if I now said if t is a linear map and it satisfies homogeneity, now sort of virtually erase the right t of 0, and now I want to go t of 0 times v. From homogeneity, if this is a linear map, what do I know is true? That's 0 times t of v, isn't it? So this piece is the homogeneity. Property. But from proposition 1.4, I can apply that to this right. T of v is just a vector, isn't it? And now it's being scaled by the 0 scalar. So what's happening over here? By Prop 1.4, this is 0, isn't it? This is the 0 vector. And this equality is again from proposition 1.4. And so now what does that allow us to conclude? If we now look at the second and the fourth entry in this string of equalities, what have we now said? If we have a linear transformation on the additive identity or on the 0 element, it needs to map to the 0 vector. So this is the 0 vector, and that equality, that string of equalities, now tells us that if we have a linear map and we apply it to the additive identity or the 0 vector, it better produce, if it's a linear map, it better give us back the 0 vector. And that did not happen with this translation map, did it? We started with the 0 vector, and it did not give us the 0 vector out. It gave us 1, 2. Suppose now that I'm looking at Q. No. Let me move on. Let's now look at something that we will talk about later, but we'll also use that here as a particular sort of map. What about norms and linearity? And this term we'll learn more about later. Well, we'll define it here, but we'll play with it more in the future. But for today, I just want to use it as a particular way of going from basically doing a dimension changing type map. So let's assume for defining norms, suppose we say x, our vector, is now this vector that has Nevada coordinates, x sub 1, x sub 2, up to x sub n, where each of these coordinates are coming from our field, F. Let's define some of these norms. Suppose I now say that the one norm, we will label norms as two vertical bars bounding or surrounding our vector x, and I'm going to say the one norm, I'm going to represent that by a subscript 1. That will be defined as we first take, and remember x, these coordinates in our, I'm sorry, the x sub 1, x sub 2, the coordinates belong to our field. And so when I say something like the absolute value of x sub 1, that's either the sign of a real number or it's the magnitude of a complex number, whatever x sub 1 is living in terms of its field. So the one norm, I take the length or the magnitude of that coordinate x1 and I raise it to the first power. This is just to sort of establish the notation or the context of what I'm doing. The second coordinate, I take its magnitude and raise that to the first power. And I just keep doing that for all coordinates. And then I take and I sum those, and then I take the first root of that sum, which means I'm not doing anything in the one norm case, but I'm just adding up the magnitudes of the coordinates. But this will hopefully make a little bit more, or be a little bit more interesting when I start increasing the norm number, the 2 norm. Now that is going to be, by notation, 2 vertical bars with a subscript 2. And this is really what you're used to thinking when you think of a norm or the Euclidean norm. This is like in 2 space, this is the hypotenuse of a right triangle, where your x and y coordinates are the sides of that right triangle. This is now the Euclidean norm. X2 is now, if we use the same strategy, we take the magnitude of x1, or its modulus, and then we square it. We take the second coordinate, its modulus, and square it. And we just keep going, and we take now the nth coordinate squared, and we sum all of those squared magnitudes up, and then we take the square root, or the 1 over nth root of that sum of squares. So this is the square root of the sum of the squares of our coordinates. That's the 2 norm. And if we wanted to, we could sort of label that as the square root of the sum from I equal 1 to n of x sub I squared. Another way of denoting what the 2 norm is. Do you see what the 3 norm would be? We take the magnitude, cube it, sum those cubes, and then take the cube root. What if I now kept going and kept going and kept going until I was looking at the infinity norm? And I said, oh, what's the infinity norm of the vector x? What's going to happen? Now we look at we take the magnitude of each of the coordinates, we raise that to the infinite power, and what's going to happen? After you take the infinite root, or after you take the or once you raise the magnitude to an infinite power, what's going to happen to sort of the relationship between these coordinates? The largest one is going to dominate, isn't it? So the one that has the biggest size, the coordinate with the biggest size is going to be the biggest when you raise it to the infinite power. And then you basically get rid of that power of infinity by taking the infinite root of that, and so you're left with the dominant coordinate in that vector x. So the infinity norm is really just taking the maximum coordinates, or the coordinate that has the largest magnitude. That's the infinity norm. So those are some definitions of norms. What I want to do now is ask, is the 2 norm linear? Question? Zero to the zero. What is that? So if you take any number and raise it to the 0th power, what is that number? That's 1, isn't it? So it's really sort of a non-norm. I wouldn't even mess with that one because now everything is going to sort of look the same. You want norm to give you sort of a size of a vector. And if you did the we don't go any lower than the 1 norm. I haven't seen a 0 norm. So we won't play with a 0 norm here. But what about the 2 norm? Is the 2 norm linear? Let's look at an example. So we can do this mapping. We can say T is a map such that, let's say, we take R3 into R. So now we're saying T is a mapping from R3 to R. And now we want to sort of ask, is it possible for T, this mapping, using the 2 norm? That's really what the 2 norm does. Let's say we're starting with little n, Nevada is 3. We now have 3 coordinates. We want to see, is this norm operation a linear map? So here we want to show or demonstrate why T, which is the 2 norm, is not a linear map. So here, is the 2 norm linear? The answer is no. And now we just have to come up with one example, a counterexample. And that counterexample is that we can show, let's say that one vector in R3 is 1, minus 1, 1. And y is 1, 1, minus 1. We can show that x, y yields the following. What if we looked at the 2 norm of x plus y? What is x plus y? 1 and so we just do a component-wise addition. And the first coordinate, 1 plus 1. That's 2. So now we're looking at 2. What's the second coordinate? Minus 1 plus 1. 0. What's the third coordinate? 1 minus 1, that's 0. We're looking at the 2 norm of that, which is what? We square 2, giving us 4. We square 0, add that to 0. We have 4. Square root of 4 is 2. And over here, if we look at the 2 norm of x, that's now the 2 norm of 1 minus 1, 1. What's that going to be? We now have the norm of 1, which is 1, squared, which is 1, plus minus 1, magnitude, 1, squared is 1, plus 1 squared is 1. So we have 3 1s added up. Or this is now, and then we take the square root of that. What about the 2 norm of y? Y had 1s also for its coordinates. And so that will be equivalently the square root of 3. And I think that you can see that if we added the square root of 3 plus the square root of 3, that's 2 times the square root of 3, and that's not the same as 2, is it? What's the square root of 3? 1.7. 2 times that is about 3.4. So this 2 is not equal to 3.4, so additivity is not satisfied for this norm mapping. The 2 norm takes us from R3 down to R, and in this case, additivity is violated. And so that's a way of showing that this 2 norm is in fact not a linear map. Let's look at something that will really make your head hurt, maybe. So I'm going to do it with an alert. And talk about an abstract concept, which is the following, that we can actually turn linear maps into a vector space. An interesting development is that we can turn the set of linear maps, which we're calling L of VW, given an input vector space V and an output vector space W, the set of linear maps, which we're labeling as script L of VW, into a vector space. Meaning if you really wanted to start getting out there in terms of a thought experiment, this one's a little bit more abstract. What do we need for a vector space? What properties need to hold? So now for a vector space, we need to have basically three things, right? We need a set that has associated with it addition, vector addition, and scalar multiplication. That's our vector space. So here we have, and now we're saying that this collection or this set of linear operators actually can be classified as a vector space. We have a set of, in quotes, vectors. Those are, in fact, the elements that belong to this set of linear maps, L. And we also have a set of scalars let's say, from our fields of reals or complex numbers. And now we need our two binary functions. One is vector addition, and the other is scalar multiplication. Where the vectors are now elements in this set of linear maps. Suppose I give, or just sort of take, two linear maps, S and T, from the set L of V comma W. Then we can define S plus T that belongs to that same set of linear maps, where S plus T operating on V is defined to be S operating on V plus T operating on V. And that can hold for all vectors in our input vector space, capital V. So there's a definition of vector addition. And our second scalar multiplication, we can say for alpha that belongs to our field F, then T is an element from our set of linear maps. We can now say that alpha T, since that is just a scaled version of the map T, we can say then that alpha T applied to the vector V, we will set or define to equal alpha times T of V, and that's our scalar multiplication. So this set of linear maps can actually be then a vector space. Now, here's a question to end on. What is the additive identity of the vector space L of V W. What's the additive identity? Such that if we added this, if this was up here, and we said, oh, let's let T be our additive identity, then if we did S plus T, we need to get S. What's going to be the additive identity? Is that believable? The zero map? So we will pick up at that point, but just think about what that means. If you now have this zero map, which was one of these concepts we did talk about earlier, but now in the set of all linear maps, the zero map would be the additive identity. And we'll pick up at that point on Monday.